Thanks, everybody. So in this video, we are going to explain the bifurcation diagram for the logistic. Okay, so in a previous video, we have already explained the bifurcation diagram for continuous systems. There we used the Lorenz system as an example. So here we are going to discuss about discrete time. Okay, in the description of the video, I'm going to put MATLAB codes to simulate your own bifurcation diagrams. So you can find MATLAB links in the description. So let's begin. Okay. First of all, we are talking about discrete time systems, right? So let's give the basics. Remember, in discrete time systems, we have a system that evolves not as a flow, but as a discrete series of steps, okay? So here we are talking about time series, right? A little different from continuous time. So the index here is I, so it goes from I plus 1, I plus 2, and the state of the system, is a time series, which means that it consists of some discrete values like xi plus 1, xi plus 2, and so on and so on. Okay. So there is no sense of flow here, right? Uh, Time here, usually, if it is used to denote something, it's used probably to denote, for example, seconds, minutes, months, years. So it references some discrete steps. And the whole idea here is that we are using discrete time systems to model evolutions that we can observe usually in discrete instances. That's why it is more common in biological systems, in economical systems, where you may, for example, observe some values over a month. So, you have for a whole year just 12 measurements, or maybe over a minute, or depending on the system, of course. So it's very different, for example, from where you want to model a flow like a mechanical system. So when you have like a spring mass damper system, obviously this is a continuous simulation. The system goes up and down as it moves within each individual second, but this is more different than having, for example, a biological population or an economic model and observing, what happens in each state during each month, for example. Okay. Um, so obviously, since the time is discrete, there's no differentiation, right? So there is no derivative, there is no velocity, there is no acceleration here. So we don't differentiate these systems. And actually, in order to describe such a system, we don't have the so-called differential equations. We have something else, which is called a difference equation. And in this difference equation, the evolution of the system in each state, let's say the current state that we are right now, xi, it depends on some function of the previous state. So this is the general formula for a differential equation. Okay, xi equals f of some function of x to the I minus 1. Okay, which means that the way that I'm going to behave in this time instance actually depends on my previous value, okay, xi minus 1. So that's the way to describe difference equations, right? And the cool thing here is that since there's no differentiation, it is much, much easier to actually obtain a solution here because you can simulate such a system with a simple for loop, okay, instead of an ODE simulation, like in MATLAB. So it's much easier to obtain solutions for discrete time systems. Now let's talk about the logistic map. One of the most famous maps in chaos, actually, I think in discrete time system, it's the simplest map that can generate chaos. So it's almost as famous as the Lorenz system. It is a very simple formula. Okay, you can solve it iteratively. As you see, xi depends on r, which is a parameter, times x to the I minus 1, the previous state, times on this term here, which is 1 minus xi to the minus 1, right? So let's see some details. Actually, it is a discrete time system, obviously. It is one-dimensional, so you have just one state. It is extremely important to note here. In continuous time, you need three states for chaos, while in discrete time, you only need one state for chaos. We have a single parameter, r. The classic values are from 0 to 4, because for higher values, we obtain instability. And the initial condition, which is x0, that goes from 0 to 1, because for higher values, again, you obtain instability. So how can we solve this system, okay, and obtain its solution? First of all, the solution is a time series, right? So x0, x1, x2, x3, x4, and so on. So to obtain the solution, we only need to know two things. The starting point, x0, right? And the parameter value r. So once I know these two, keys, which are actually, the hidden information as you like in encryption, we can go and solve the time series. So for example, x1 is r times x0 times 1 minus x0. Once we obtain x1, we can obtain x2. It's r minus r times x1 multiplied by 1 minus x1. x3 is r times x2 multiplied by 1 minus x2, and so on. And you can simply, simulate this in a for loop and obtain how many values that you like. So extremely easy, right? Much easier compared to the compared to the Lorenz system. So this system is extremely simple. I mean, as you can see, it's just a couple of terms, but due to the simple non-linearity that it has, it showcases a collection of very rich dynamics, similar to the Lorenz system. So let's talk about the rich dynamics of the system. The rich dynamics depend on the value of the parameter. So this control parameter affects the way the system behaves. So let's see what happens. If the parameter R here is generally from 0 to 1, so it takes values smaller than 1, the behavior we have is that the system converges to a fixed value, okay, to an equilibrium, as you like. I mean, if you are familiar with the term. So here, for example, a simulation for R equals 0.9, you see that the system starts from here, and after some iterations, remember, these initial iterations are called transient behavior. And once the system stabilizes, we call this steady state behavior. And we are interested in the steady state behavior, okay? So this time series goes to 0, right? Even if I chose another initial condition, again, I would end up going to 0. So in this case, where the system actually stabilizes to a single position, we can say that it has a periodic behavior and the level of the period is 1, right? So this is called period 1 behavior. We say this because the system stabilizes to a single fixed point, the equilibrium. What happens if I increase the parameter, right? If I go from higher values, let's say the parameter is from 1 to 3, then the system again has period 1 behavior, but it doesn't go to 0. It goes to another point. It's the point r minus 1 over r. So here, for example, again, you can see a simulation for r equals 2.8. I start from here. I have this initial, transient behavior where I oscillate a little bit, and then I end up in a steady state. So again, the system stabilizes into a single point, and we can understand that this behavior is, a period 1 behavior, right? Now what happens? After we increase the parameter a little bit further than 3, we have, you know, many different behaviors appearing. So let's see. Actually, what we have here is a transition from periodic behavior of different levels into chaos. Let's see that. See what happens when I set R equals to 3.3, right? So I simulate the system from here. I have another very small transient, but see what happens. The system ends up, of course, being bounded, and it oscillates between two different states. I have named them here. It's state 1 and state 2. So it goes back and forth. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And it remains this way throughout. Okay. So this behavior, as you can understand, is periodic, but on a different level. We call this period 2, right? Because the system requires two transitions to go back into its initial state. It's first state, second state, and then it goes back to the initial state again. And this repeats again and again. So this is a period 2 behavior. Okay, so notice we went from period 1 behavior to period 2 behavior. See what happens if I increase the parameter a little more. Oops, for 3.5, see what happens here after the transient. Again, I have a periodic behavior, but the level is different, right? Now, I have a period 4 behavior. So I oscillate between 4 different states. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right. So you see how the behavior changed from the previous case. We have again periodic behavior, but on a different level. We went from period 1 to period 2 to period 4, right? What if I increase the parameter a little bit more? Let's say I put it to 3.56. Here we have an even higher periodic behavior. It's actually period 8. So the states are 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. and it repeats again and again. Okay, so we have increased the period. By the way, if you think they are close enough, they are not the same. So if you zoom in, 1 and 5 is a different state, 3 and 7 is a different state, okay? Because uh, if you zoom out, it may seem like it is a period 4. No, it is actually period 8 behavior. I have checked it, I'm pretty sure. Okay, so you see that the period increases and increases and increases as I increase R. So if I increase it a little bit more, what happens? We go to period 16, period 32, period 64, and over a very, very small interval, something amazing happens. We transition into chaos. Okay, so for example, for R equals 4, what do we have? I have this solution right here that it seems to be with no clear pattern. And that's the case. The system here doesn't have a periodic behavior. We have an absence of periodicity. Okay. Uh, the behavior here is without a specific pattern. Okay. I have plotted here 80 values, but even if I plot 800 or 8,000 or 80,000 values, the trajectory will never fall back into itself and repeat itself. Okay. So it seems completely erratic. And that's indication that we have chaotic behavior. Okay, so this time series that you see here is chaotic. Okay, for this specific parameter. So this amazing thing happened. We transitioned slowly but steadily from period 1 to 4, 16, 32, 64, and so on until we went into chaos, right? And now that we're in chaos, we have this amazing phenomenon that you all have heard. It's called the butterfly effect. And this phenomenon is called this way because it denotes the sensitivity to initial conditions. This is the butterfly effect right here. Let's explain it. I have, apologies, I have two different simulations for the same parameter, r equals 4, and two only slightly different initial conditions. Okay, so see, x0 is 0.1 for the blue trajectory, and 0.1 plus 10 to the minus 16th for the second trajectory, right? And these two trajectories practically start from almost the same initial point, right? And for the first couple of iterations, let's say 40 iterations, I mean, they look completely similar, right? You cannot even see the blue trajectory because it is under the red one. But slowly, very, very slowly, but surely, after like 50th iteration, what happens? This very, very small change, I mean, it is extremely small, okay, 10 to the minus 16th, started becoming a little larger, a little larger, a little larger. And then at around 50 iterations, we see that these two trajectories start diverge, significantly diverge. And after the 50th iteration, become completely irrelevant. Okay. So this is the butterfly effect right here. The butterfly effect tells us that minuscule changes in the system settings, like the initial condition, will eventually lead to cataclysmic changes in its behavior. And that's what we see right here. The two trajectories eventually become completely irrelevant from each other, right? So this amazing phenomenon indicates chaotic behavior. Okay. So as you see, the logistic map is very simple, but actually it has a collection of many different interesting behaviors, right? So the question here that arises is this: can I have a diagram that helps me understand where the map behaves the way it behaves? Okay, so this is the bifurcation diagram. You may have seen it, of course, because it's very famous in popular culture. So you may have seen it in book covers or maybe in video clips. I guess it appears, right? But what is it? Okay, it is a two-dimensional graph, and the idea behind the bifurcation diagram is this. On the x-axis, we have the parameter values that are interesting to us. Let's say R, for example, right? And on the y-axis, what we plot is the steady state. So we discard the first values and we only plot the last values of the time series. And we plot them vertically. Okay, so the idea is that for each parameter value, we look vertically at the diagram and it will immediately tell us how many values do we have in the steady state. Do we have one? Then we have a period one. Do we have two values? Then we have a period two. And this is a very simple idea to look at the diagram and understand that for this value, I have a period two. For this value, I have a period four. For this value, I have a period 16. For this value, I have chaos, right? So this diagram gives us an exact information about how the system behaves. But moreover, it also tells us how it transitions to chaos, right? So it gives us another very, very useful information. So let's see what happens. Okay, this is a pseudocode for plotting the diagram. Let me explain it. So we begin by choosing a bifurcation parameter of interest. For our map, let's say r equals the r parameter. Okay, so we initialize everything else. Let's say the system has more parameters. We set a value for them that we desire. We set a fixed initial condition, x0, and then we choose a bifurcation interval. Okay, so let's say I want to study my parameter from 0 to 1. Okay, actually, we're going to study it from 0 to 4 in the logistic case. Okay, and we also choose an iteration step, which means each time how much forward we progress in our simulations. Okay, the smaller the case, the diagram will take a little bit slower to compute, but it will be a bit more detailed, right? So then we have a simple for loop. We go into the for loop, and what do we do? Let's say we start from r equals 0. We compute a large number of iterations of the map. Let's say we compute 1,000 values, right? And for this 1,000 values, let's say we plot the last of them. Let's say we choose 100 values. So let's say we plot the last 100 values of the time series vertically on this point. So on the graph, we go to this value r equals 0, and we plot vertically the last 100 values of the map. And this will show us if the map has, in these 100 values, we have like one repeating value or two repeating values or four or six or 12 repeating values, or we have 100 different values, okay, which indicates chaotic behavior. So then we iterate the parameter r, we increase it a little bit, and then we repeat the forward loop, the for loop, I'm sorry, until we reach our final value. So if we run this code, which by the way is available in the description of the video, we will end up with this great diagram. Okay, so this is the bifurcation diagram for the logistic map. And this diagram immediately gives me information about where the map is chaotic and where it is periodic. So all the points that are right here, indicate steady state behavior. And remember, you look at this graph vertically. Okay, so for example, for r equals 2, I have 1 point, which means that the map ends up in a period 1 around 0.4. For r equals 3.2, I have 2 points, which means that the map has a period 2 behavior, and these are the 2 points, if I plot them, around 0.8 and 0.5, which are the 2 periodic points of the system. And the dense regions are chaos. Let's see it. So for r equals 2, for example, this single point, as I said, indicates that the system has, after the transient, a steady state behavior of period 1. For r equals 3.1, as I said, these 2 points right here indicate that after the transient, the system has a steady state behavior of period 2. For around 3.5 that were right here, these 1, 2, 3, 4 points vertically, and this indicates that the system has a periodic behavior of period 4, as you see right here, 1, 2, 3, 4, 1, 2, 3, 4. For the dense regions, which indicates that we have many, many points in the steady state, for example, for r equals 4, these dense vertical spots right here indicate that the system has a chaotic behavior, right? As you see right here, no distinguishable pattern. So by looking at this diagram, I can immediately understand what happens for each parameter value. And also, I can also understand, right, how I transition to chaos. So looking at that, I can understand that when I increase the parameter r, I go from period 1 to 0, actually, to the steady state of 0. Then I go to period 1 in a non-zero equilibrium. Then I go to period 2. And then I go to period 4. And then I go to period 8. And then I go into chaos. And these white spots right here indicate that I actually go on and off from chaos. So sometimes I am in chaotic state, but then I transition to a non-chaotic state. So let's see in this region and in a little bit more detail. I will zoom in into this part. Let me show you the zoomed in region. So this is the zoomed region from 3.5 to 4. And you see that I transition to chaos but I have some gaps here. This means that as the system is chaotic, as I increase the parameter, I may end up going to a non-chaotic state. So for example, here I have a chaos, right, for 3.80 something. And then if I increase it a little bit longer, I go outside of this region, which means I go into period 1, 2, 3. I go into period 3 from chaos, okay? This is called crisis, by the way. And you observe this very nice pattern. It's actually a fractal pattern. And if you're gonna go into a little more detail, you can zoom in into subregions and compute the bifurcation diagram in a more detail, and you will observe repeating patterns. So for example, if I choose this region right here and I zoom in, you see this sort of period doubling root appears again. So it has sort of a fractal pattern. You know, I zoom in and I observe the exact same transition into chaos, right? And if I'm really obsessed, I can zoom in even further. So let's put this very small point right here. And you see that again, if I plot it in detail, I observe again a great transition into chaos, right? Through a period doubling route. And again, if I'm like super obsessed, I can go into this very small region, zoom in, compute the bifurcation diagram in detail, and this is what I get. And you see that these are very similar shapes, right? So the bifurcation diagram shows a very fractal-like repeating pattern in its behavior, right? And of course, if you are really crazy, you can zoom in again and again and again. You will always observe the same phenomenon. So simple map in its structure, but extremely powerful and extremely complex dynamics, right? This is an amazing phenomenon in chaos. So this is one example of how the bifurcation diagram works. I hope you can have understood how this works. Of course, you can compute it for other maps as well, and different maps showcase different phenomena. So for example, this is another well-known map. It's called the sign map. If you Google it, you will immediately find which map is this. And it has a different bifurcation diagram. Very interesting phenomena appearing. So look at that, for example. You see how this it shows chaotic behavior here, and then the attractor goes into a much wider width. Okay, this means that we have, again, this is called usually crisis of the attractor. So for example, for this value right here, the system is chaotic and the values go from 0 to 1, right? But if I increase the parameter a little more and I go here to 1.1, for example, again, I have a chaotic behavior, but what is the difference from here to here? Here, in the second case, we have again chaos, but now the map values go not from 0 to 1, but as you see, from around minus 1.2 to 1.2. So we have, an explosion of the attractor. The attractor becomes larger, right? And here, this phenomenon that also appears in the logistic map. Let's see what happens. For this range around here where you see dense dots, I have a chaotic behavior, but if I increase the parameter a little more, let's say to 1.40 something, I have this case where I drop into period 2 behavior. This phenomenon, for example, is called crisis. Crisis happens when I have a chaotic behavior for one parameter value, and then I increase the value of the parameter a little bit more, and I go very quickly out of chaos. So I drop from chaos to period 2, right? And of course, it can happen the other way around. So this is another interesting phenomenon, which is called crisis. So as you can understand, numerous interesting phenomena appearing in chaotic maps, right? So I'm gonna put a code for a bifurcation diagram in the description. Any comments or questions that you have, you can write them in the comments of the YouTube video, and I will try to reply to every one of them. So thank you very much.